Hey, and welcome to my presentation of my research on multi-food items detection and localization in images. I'm Matthew Morgan, and I'm supervised by Patrick Donnelly at Oregon State University, where I study computer science. So as an introduction, my research is centered around the following question. Does machine learning have the potential to change cafeterias for the better by tracking nutrition and food waste? And we can start by thinking about problems that might exist in cafeterias. If we start with nutrition, according to the Agency for Healthcare Research and Quality, malnutrition in the United States affects more than 30% of hospitalized patients, and patients with malnutrition are 50% more likely to be readmitted to the hospital within 100 days than those without malnutrition. And if you think about the hospital cafeteria, if we can measure how much food a patient consumes, then we can notify a nurse when we believe they're at risk for malnutrition. And food waste is another problem with cafeterias. In the United States, it's estimated that 31% of the available food supply went uneaten in 2010, which represents 133 billion pounds of food and about a loss of $161 billion at retail prices. So say at a school, for example, if we could measure how much food is thrown away uneaten, then chefs could alter their menu or decrease the portion sizes of wasted dishes. So ultimately, our goal is to track nutritional intake and food waste in hospitals, schools, and correctional facilities. Our foundational aim is to take this huge problem of reducing malnutrition and food waste and break it down into small steps, and first just detect foods on a plate. And this is illustrated in the image in the middle. Each box identifies a food, and the number next to the name of the food represents the confidence of the model in its prediction. So this is what an AI model might detect, how it might detect foods. And if it says this is pasta with red sauce, 0.95, that means it's 95% sure that that is pasta with red sauce. And the exciting thing is we're using this in a partnership with St. Charles Hospital in Bend, Oregon, to conduct a trial study at the end of the year. So to get to that aim, we first prepare a data set for a machine learning model. And to best prepare for our work with the hospital, we scoured the internet and found that there aren't many data sets with American food available that you'd find online, but there are two publicly available data sets, one primarily Japanese food and other primary Italian foods that have some foods found in America that we can use in our American cafeteria food data set. So we selected 12 foods from each data set, 12 from the Japanese one, 12 from the Italian one. And there's actually 6 classes from both that overlap. So we merged those together, and the result is 18 distinct food classes with a total of 2,891 images. And that's 3,839 targets of the 18 classes. And a target is simply a box around the food is a target. So in this image, there's 1, 2, 3, 4 different targets. And if you say you have 2 slices of pizza and each is a target in one image, you could have 2 targets in one image. So that's why there's more targets than images. Now, to test our model accurately, we perform a 70-20-10 split into train, test, and validation sets. And the split is stratified so that there's an even distribution of classes between the train, test, and validation sets. And that 20% test set is held out so we can test our model on images it's never seen before and try to get a good idea of the accuracy it would have on real life data. Here's a more detailed overview of our data set. You can see that this lists the classes. On the left side is the Japanese foods in that gray circle. On the right side, the gray circle is Italian foods. And in the middle of the Venn diagram is pizza, bread roll, French fries. Those are all the classes that are merged together. So those are come from both data sets and are combined. And these are all fairly common foods that I think you'd see in a American cafeteria. There are some other foods on the outside of the orange circle that are not included in our data set. We've held those out because they're not very common in America, and we could use them in the future if we see something specific on the menu that we want to train a model for. And this is even more detail of those 18 classes. If I get the laser pointer, you can see that white rice is the max count of targets for our data set with 677. And all these in the top 6 are merged together from both data sets or combined. And then this section is from the Italian data set, nothing from Japanese. And the min here is 36 for P's, which is not very much. And then down at the bottom is the Japanese food data set. And there's a good range from 102 to 169 targets per class. In total, we have 2,219 from the Japanese food data set and 1,620. Now, to actually train the model, we use YOLO-R, which is based off of the YOLO framework, and it's an acronym for You Only Learn One Representation. The model uses the PyTorch framework, and it's available on GitHub. The authors represent the Taiwanese Institute of Information Science, Academia Sinica, and Elan Microelectronics Corporation of Taiwan. And the YOLO-R model uses an approach to combine explicit knowledge from the data set with implicit knowledge learned subconsciously, which attempts to mimic mammalian brains. Say, for example, humans, we can process explicit knowledge using our eyes. If I see an apple, it's using my eyesight with explicit knowledge, but also implicit knowledge, which is like our memories and things we've seen before. And combine those two, I can say, see an object. It's definitely an object, and I've seen something like it before, so that's an apple. And we use the default parameters for training, which are on the screen and listed in more detail in the GitHub repo, but they are the defaults. And then for our results, after training the model for 300 epochs, we have 0.917 overall mean average precision at 0.5 IOU and 0.721 overall mean average precision at 0.95 IOU. IOU is the intersection over union, and it's essentially a metric of how accurate the model's guess is, and at what point do we count it as a good guess or as a true correct guess. And that's explained in figure 3. You can see that you divide the intersection of box 1, say that's the true value, and box 2 is the predicted value by the model, and divide that by the union of the true value, union the area of the predicted box. Divide these two, you get the IOU. So the higher the IOU, the better the guess is by the model, because the intersection will be larger and the union will be smaller. And we mainly just focus on the mean average precision at 0.5 because we don't need our guess to be super pinpoint precise in terms of where the box is located. We just want to make sure that we have the right class and good confidence in that, because in the future, we plan to develop more models that can actually estimate the volume of the food and exactly where it is. But this is more just for classification of the objects on the plate. And you can see in figure 4 that our recall on the right is actually a bit better than the precision, which kind of drops off. Overall, it's still good, but it means that we have a few false positives more than false negatives. And I'll explain that in a couple slides. This is a little bit more of a detail on our results, and they seem promising because the bars in black are from the Italian foods data set. The bars in yellow are from the Japanese food data set, and the bars in orange are the ones that we combined from both. And the orange ones are pretty well distributed, showing that the merging of the classes is totally doesn't hurt accuracy too much. It seems that the mean average precision is kind of a mix between the two, and it's not way better or not way worse. It's just a nice way to add extra training data. And also, if you look at the item count on the top of the graph, you can see that more data is not necessarily better. It's a little bit more important to have good quality of data. And it's going to be important to note that having more data usually the model generalizes well, but it doesn't always increase our accuracy as much as we hope. So in the future, we want to focus on having really quality data to train the model with, and enough of it to generalize well. Now I have a few more slides left. This is a example of what our model can detect, and this is from the test set that was held out. So these are images the model had never seen before training. And overall, the model does well. You can see that there are some false positives. If you look in the stars here, there's 2 bread rolls here, and the model actually predicts there's 3 bread rolls. So one of those bread rolls in the middle is a false positive. So that one is an incorrect guess. And there are a couple other cases of this happening, such as the green beans up here. There's 2 boxes instead of 1. A way that we could fix this is to increase our threshold for a prediction. Right now we have it at 0.2. So anything less than 0.2 doesn't count as a prediction. Maybe if we increase this to 0.5, this 0.3 would get it go away, and we wouldn't have as many false positives. So something that we're going to implement in the future. Another thing is that this shows problems we might run into, such as identifying carrots. If you look at the stars in this image, the carrots here are shaved and they're shaved here, but this is mixed salad and this is carrots. So you kind of wonder, like, the model should probably predict shaved carrots here, but it only guesses mixed salad, which is correct. But something to keep in mind, because food is prepared in very different ways. And if the food is prepared in a way that the model doesn't expect, it's probably not going to be detected. The carrots up here are kind of circular cut up carrots, and the model detects like every single little carrot, which is really interesting, but the actual correct value is just one big box around all the carrots. So just like this, a box all the way around the carrots should be the way you should do it. But the main thing is that we want to make sure that we have a menu of the cafeteria before we implement our model, so that we have an idea of what the kind of foods are there, and then also maybe take some pictures and see what the food preparation looks like for these meals, and are they going to be consistent. So for the conclusion, ultimately combining the disparate data sets worked well with high accuracy, and we plan to use this more in the future. The good results are pretty good with very few images. So it makes sense that this model will be effective in the future. When we get even more training data, it'll only increase the accuracy, and just overall add more classes will provide a more robust model for a cafeteria. I built a pipeline for successfully using this model of doing object detection. It's an API that can be used on any computer, and we plan to implement a Raspberry Pi to take pictures and send it to the cloud in cafeterias. And for future work, before our trial with St. Charles Hospital, we will collect data at Oregon State University cafeteria and use that data as a trial run to improve our model and see how it works, how it does in a cafeteria at a small scale before going to the hospital. And lastly, this is a flowchart diagram of how we expect our trial to go. We are going to put the food under the camera and take a picture of it, record the weight of the food too, and scan a QR code on the plate so that we can save that plate ID for later. We'll send the data to the cloud and run a detection on it. Maybe get an image with those bounding boxes that I showed you earlier and display that to the consumer so they can see how their food is being used for research. And then once the food is consumed, we go back to the cafeteria camera, put it under the camera, and take a picture again of the leftover food, and do the same thing, record the weight and the QR code. And now we can compare the before and after of before it was consumed and after the food was consumed, and take the difference of that and see how much did the person eat. And then using that weight and camera, we can detect what foods are uneaten and which ones are thrown away uneaten, and maybe notify somebody that, hey, these foods are uneaten, and if we change the menu, we can decrease food waste. We hope that this work can be valuable to cafeterias, and here's the works cited for the works that I've cited in this presentation. And thank you so much for attending my presentation.